Before watching this video, please subscribe this channel and click on bell icon to get the notifications for the upcoming classes.
Welcome to thermodynamic classes. In this class, I want to explain you PV and TS diagram of Otto cycle, and also I want to derive the efficiency for the Otto cycle. So Otto cycle, so it consists of four processes. So 1 to 2, 2 to 3, 3 to 4, 4 to 1. So during this process 1 to 2, so compression takes place in adiabatic process. So that's why 1 to 2 is called as the adiabatic compression. So during this process, volume is decreased and pressure is increased. So you can identify this in PV diagram. So in this diagram, PV diagram, so volume is decreased from V1 to V2. Whenever you identify this in TS diagram 1 to 2, so entropy is constant, as adiabatic process is called as a asentropic process. Entropy is constant during this process, that is S1 is equal to S2. So S1 is equal to S2. So entropy is equal to constant. So temperature is increases from T1 to T1 to T2. So here only compression takes place. The air supplied inside the cylinder gets compressed during this process. So after 2 to 3 is the process of constant volume heat addition. Here you can identify this in a PV diagram as a vertical line, that is V1 is equal to, so V2 is equal to V3. So here that is the straight line, vertical line. So here volume is constant during this process, but heat is added. This is very important process in Otto cycle. So heat addition is the very important process, as heat is supplied to the air in this cycle, in this process only. So as the constant volume process, heats in constant volume process, heat supplied Q1, that is Q1 is equal to, as the mass is taken as a 1 kg, so Q is equal to mCV. So temperature, that is temperature change is, so T2 to T3, that is higher temperature, that is T3 minus, so T1, T2. Yes, so here the end states are 3 and 2. The general formula we commonly used, so mCV T2 minus T1, but here the process is in between the 2 to 3. That's why I change this line, that is T3 minus T2. This is Q1. So in the process of 2 to 3. So in the process of 2 to 3, heat addition takes place. That's why, so Q1 is equal to CV T3 minus T2. Next, so 3 to 4, adiabatic expansion. So after heat addition, the air is expanded from 0.3 to 0.4. So here volume is increased from, so V3 to V4, and pressure is decreased from P3 to P4. At the same time, temperature also decreased from T3 to T4. So it is also represented as a vertical line in TS diagram, as a curved line as in PV diagram. Next one, 4 to 1, constant volume heat rejection, So heat is rejected to the atmosphere here at a constant volume, that is Q2, that is 4 to 1 process. Q2 heat rejected is equal to CV, so higher temperature T4 minus, so T1. Okay, so here here the heat rejected is Cv T3 minus T2. So heat supplied is equal to Cv T3 minus T2. So heat rejected Cv T4 minus T1. So that is the this is about the PV diagram and TS diagram of Otto cycle. So 1 to 2 is the adiabatic compression, 2 to 3 is the constant volume heat addition, 3 to 4 is the adiabatic expansion. So 4 to 1 is the constant volume heat rejection. So here, so we must note the heat supplied, heat addition Q1 is equal to CvT3 minus T2. So at the same time Q2 is equal to, that is the heat rejected, so Cv T4 minus T1. Now we are going to calculate the, so Q1, that is Q1 is equal to Cv T3 minus T2. So Q2 is equal to Cv T4 minus T1. That is, if that work done is equal to heat supplied minus heat rejected. These are the basic formula, that is Q1 minus Q2. At the same time, what is the efficiency? If you want to derive the efficiency of an Otto cycle, so work done by heat supplied, that is, so Q1 minus Q2 by Q1. So whenever you applied, so that is Q1 is equal to Cv, so T3 minus T2 minus Cv T4 minus T1 by Cv T3 minus T2. After subtracting, dividing this with the these two terms, so we will get, that is 1 minus T4 minus T1 by T3 minus T2. So this is the efficiency of Otto cycle in terms of temperatures, if the temperature is known. So but here some another conditions are there, that is very very important relation is the expansion ratios, compression ratios and expansion ratios. So here this is the, in this diagram you can identify that. So V1 is equal to V4. So I explain you separately. So here, so in Otto cycle or diesel cycle, so compression ratio and expansion ratio is the very very important factors. That is compression ratio, RE, expansion ratio. So these are the very very important terms in Otto cycle and diesel cycle. So in diesel cycle another term, that cutoff ratio is also there. I will explain you later about that. So in this I want to explain you about the compression ratio before proceed to the derivation. So RC, that is the compression ratio. What is compression ratio? So here volume during the cycle, during the process 1 to 2, so volume is decreased from V1 to V2. This decrease, that is the volume is decreased, compressed, that is how much so that is V2, V1 to V2. So this ratio is called as compression ratio. At the same time here, so 3 to 4 is the expansion process. Here also volume is decreased from, so volume is increased from V3 to V4, but so it is taken as in terms of, so V4 by V3 is equal to RE, expansion ratio. So volume changes in volume. So change in volume, RE. So that is RE is the expansion ratio. So RC is the compression ratio. But you can identify that So V1 is equal to, here V1 is equal to V4, V1 is equal to V4, and V2 is equal to V3. So that is V1 by V2 is equal to V4 by V3. That is RC is equal to RE in Otto cycle. So both in, so here the same values. That's why in Otto cycle both compression ratio and expansion ratio both are same. That's why this is taken as a simply R. R is the compression ratio. So compression ratio. So this is very important term in Otto cycle. So now we are moving to the previous matter. That is the, so if efficiency of the Otto cycle in terms of temperature. If you want to convert this into compression ratios in terms of compression ratio, so first of all we should go through the basic processes here. So processes 1 to 2, process 1 to 2. So adiabatic, the relation between the, so the relations between the compression ratios and temperature. Here we want to convert so these temperatures into compression ratios. So these temperatures into compression ratios. That's why we want to convert these temperatures into in terms of compression ratios or expansion ratios. So now I applied this 1 to 2, that is adiabatic compression. Here the compression ratio, so V1 by, so V2 is the compression ratio. So what is the relation between the temperatures and volumes in adiabatic process? That is, so T2 by T1 whole to the power of gamma minus 1. This is the relation between the volumes and temperatures in adiabatic or polytropic process. So these are explained in the previous classes. So there are some relations. There are three relations. That is, so in between the temperatures, pressures and volumes. So here this is the very important relation. So we should concentrate on compression ratio only. That is the V1 by V2 is equal to R to the power of gamma minus 1. That is T2 is equal to, so T1 into R to the power of gamma minus 1. In the same manner 3 to 4 here also. So what is the expansion ratio is here, that is V4 by V3 to the power of gamma minus 1, that is T4 by T3 is equal to R to the power of gamma minus 1. Then here so V3 by V4, then it is T3 by T4. So T3 by T4. So in opposite manner, that is V1 by V2 is equal to, so T2 by T1, and like that T3 by T4 is equal to T4 by T3, which is, so then T3 is equal to, so T3 is equal to T4 into R to the power of gamma minus 1. Here once we get relation for T2 and T3, just we are going to submit these equations into our efficiency in terms of, that is Otto cycle is equal to 1 minus T4 minus T1 by T3 minus T2 as 1 minus T4 minus T1. So the relation for T3, here T3 is equal to T4 into R to the power of gamma minus 1, T4 into R to the power of gamma minus 1. Here T2 is equal to T1 R to the power of gamma minus 1. So 1 minus T4 minus T1. Here you can subtract T4 minus T1, that is, so T4 minus T1, T4 minus T1, so this is 1 minus 1 by R to the power of gamma minus 1. So this is the efficiency of Otto cycle in terms of compression ratio. Okay, so efficiency of Otto cycle, that is 1 minus T4 minus T1 by T3 minus T2. So after converting these temperatures into compression ratios, that is 1 minus 1 by R to the power of gamma minus 1. So Otto cycle efficiency depends on the compression ratio only.
Thank you for watching this video. Please subscribe this channel and click on bell icon to get the notifications for the upcoming classes. And share this